introduce the speaker, I'd like to call upon the Waterloo Institute of Nanotechnology Executive Director, Dr. Sushanta Mitra, to give the introduction.
Good afternoon, everyone. What a crowd. I see all the young, buzzing mind here sitting in this auditorium. So it is a distinct pleasure and honor to welcome Professor Joanna Aizenberg as a WIN Distinguished Lecturer. This is one of the very special lectures that we have, for our very distinguished scholars that arrive in this campus at WIN. I'm really happy to have Joanna joining us here. Joanna Aizenberg is Amy Smith Berlison Professor of Material Science and Professor of Chemistry and Chemical Biology at Harvard. Pursues a broad range of research interests that includes biomimetics, self-assembly, smart materials, bio-nano interface, crystal engineering, surface chemistry, nanofabrication, biomineralization, biomechanics, and bio-optics. That is really a huge gamut of things that intersect with all the research that we also do at WIN. So she received the BS degree in chemistry in 1981, MS in physical chemistry in 1984 from Moscow State University, and PhD in structural biology from Weizmann Institute of Science in 1996. Joanna is the director of the Cavalier Institute for Nanoscience and Technology and platform leader in the Weiss Institute for Bio-Inspired Engineering at Harvard. She has served as the board of directors of MRS, board on the physics and astronomy of the National Academies. And she has been elected as the to the American Academy of Arts and Science, is a fellow of the AAAS. She is also a fellow of APS and MRS as well. Dr. Aizenberg has received numerous awards from the American Chemical Society, ACS, MRS, including the Fred Cavalier Distinguished Lectureship in Nanoscience and many others, as well as the 2 R&D 100 Awards for the Best Innovation in 2012 and 2013. More importantly, she has a strong connection with Waterloo. She engaged significantly with the Waterloo community. Over the past 9 years, she has hired over 40 co-op students and 4 graduate students from University of Waterloo. She is already our brand ambassador. I'm really glad to have Joanna here. And without further ado, I'd like you to come to the stage and deliver this distinguished lecture. Thank you so much. Absolutely delighted.
It's my pleasure indeed to be here, and of course being a scientist, it means I'm a geek, and I prepared a scientific presentation, although as I could see from this morning, everybody is talking about whatever they want to talk, they ask questions, and we are so narrow-minded. I really want to talk about my research, but still I did introduce a couple of slides somewhere at the beginning of my talk, or I would like to start with something that, who knows, I may not have time at the end of the lecture. And as you could see, I slightly changed the title of my lecture to more concise and more to the topic, to the things that I want to share with you. But since everybody was sharing their experience, sharing their how they ended up where they ended up, I would like to say that in addition to my studies that were already mentioned, so I won't go there, but very strange past that I had. So after having undergraduate degree in former USSR in Moscow University, then PhD in structural biology, starting as a physical chemist, then structural biologist in my PhD, then doing materials pretty much science as a postdoc in George Whiteside's group then, although pretty much everybody at Harvard when I was there was trying to convince me to go to academia. I didn't want to do it, and I went to Bell Labs. And Bell Labs was already mentioned today, such a wonderful place. And I thought that I would stay at Bell Labs forever, but unfortunately, the fact that it's not monopoly anymore, crash in market affected the research in Bell Labs profoundly. So I spent only 10 years at Bell Labs, and I was doing the more basic science that I'm even doing as a professor at Harvard. It was really basic, fundamental science that Bell Labs was happy to have as part of this their scientific portfolio. So then, again, talking about how to apply or what to do, these questions were asked this morning. I actually never applied for pretty much any job. So when I was at Bell Labs, and Bell Labs was on its decline, Harvard actually asked me to join. And that's another very unusual path. I actually didn't go through academic tenure track. I was hired at Harvard in 2007, 10 years now, as a full professor. So very strange. In addition to that, I also have very strange, unusual maybe, family history. I think family is extremely important in every possible way, but I started very early. So I actually had both of my sons as an undergraduate student, very early, so that they were already up when I needed to make my major choices in my jobs, and I didn't have to deal with babies at that time. I already have great students, as my grandson is now in first grade, so I have grandkids, and all of them are participating in our big family of scientific family. I have a very big group, although it's a little bit down. In the last year or two, it was probably 60 people at a certain moment. Now it's about 35, maybe more, but somewhere there. And while walking here, and this is what I want to show as the next slide, somebody suggested to me to do the following, to ask, even for this audience, for those who are now here in this conference, to stand up for those students who were at certain time students in my lab. How many are there? So, 1, 2, 3, 4, 6, 7, 8, 9, 10. So that's a lot. Actually, maybe I didn't see some because there is a lot of bright lights here. So that already probably tells you what is my connection to Waterloo. I love this program. I love this place. And it all started probably, I'd say, 8 years ago. Ian probably knows better. When Ian Burgess was not actually my student. He was a student in a different group, but I think he spent all the time in my lab. And my God, he was excellent. And he was telling me, you know, there's a great program. And you'll see it's a great program. And he started to hire co-op students from Waterloo to my lab. Steffi Sunny is my PhD student, just graduated from Waterloo. Michael Creda was one of the first co-op students we hired, who is now 4th year, I think, PhD student in my group. These are current Waterloo co-op students in my group now. And this, I think that the number that you presented, you said 40 plus, it's a wrong number because there might be a little bit off because there could be a couple of students here from a couple of other universities in Canada. But there's definitely all Canadian students that were in my group over the last 8 years when Ian was in my group and initiated this wonderful program. And I must say something that's probably not a nice thing to say, but I will anyway. From the moment I started to hire Waterloo students, I stopped hiring Harvard undergraduates. Not that they're not good. They are good. But there is something amazing about the fact that these students are coming committed for a pretty long time, and they spend time in the lab, and they have a project. And maybe the idea of having a deadline, whether it's 4 months or 8, something has to be done by that deadline, makes this program absolutely incredible, but also the fact that they're not distracted by classes at the time when they're in the lab. And a majority of students co-op students in my lab would end up with a paper. Those who don't have papers yet, they're coming, don't worry, especially if you were good students. So far, we didn't have a problem with any of our Waterloo students. But we did have problems with Harvard students because they're so thinly spread and they have so much to do that, in fact, their commitment often to what they do in the lab is not that pronounced. So let me now talk about nanoscience. So I'm educated as a physical chemist, and at a certain moment I decided to look at this as a statistical measure in science. So we heard a lot today about industry and startups, but let's think about academic career. Let's think about publications. So if we look at publications and we look at all papers in any science altogether, then if I look at these years, each part is this 5-year span, there's this huge number, of course. But I'll do something else now. I'll add to that graph another graph, and I would add emergence of nanoscience, and now looking in percentage, so all the papers in 96, 90 would be taken as 100, and then this is the baseline that I've shown you before. These are all together. This is a huge increase, actually. We are publishing almost 3 times more than we used to publish before. But look at that. Look at the number of papers. This is not 2.5 times more. This is now 140 times more than it used to be. So this is growth of nanoscience. There is extremely important things happening in nanoscience across many fields. Let's take a look in something else, and I'll put another graph here. And again, I'm talking about scientific publications, but they give you an idea of the importance of the field. And since then, there are a couple other fields that emerged, but not every field was as successful as nanoscience. But yet another field that I want to put on this graph is, in fact, what I would call bio-nanoscience. Not only nanoscience, but something interesting that is happening in biological systems at the nanoscale, and how that can give us interesting ideas, what to do with that. And if now, again, we look at the papers in bio-nanoscience have grown to 30% of total number of nanoscience papers. So 1/3 of all nanoscience papers are bio-nanoscience papers. And this is the area that I really like and I want to talk about. And what I will try to do now is actually share with you. As I said, I'm a geek, I'm interested in science, and I love it so much that I cannot think about presenting anything but science. I've done already introduction about something else, but now it's time to talk about science. And I'll give a couple of examples, and I don't, it doesn't matter really how far I will go in my presentation, because I wanted to show a subset of projects, and mostly talking about projects that also were presented here in the poster session. And there's 5 areas that I want to mention. But the way I want to do it, I want to start with a dream. And by dream, I mean I'm a materials chemist. What if I want to think about, imagine, not make yet, but imagine technologies that would completely change type of not only materials, but also devices and overall architectures. And then what is there that we want these things to have? And what is there is, in fact, we want them to be adaptive, and they're not in current materials. We want them to harvest energy from environment instead of wasting energy. We want sometimes them to mechanically reconfigure. We want them to collect and deliver water. We want to collect light, maybe. We want them, oh, that's a very important one, to self-heal if damage appears. And this list could be long, change color if you're into that, maybe self-clean, and again and again, repel ice, repel moisture, or maybe collect moisture if needed. And if I were, at least my drive and my feeling that how that can be solved, if we build as nanoscience is done by evolution in organisms. So if we build as an organism, and by that I mean that the small length scale defines the property on the large scale. If we think about self-assembly, if we think about nanoscale, self-organization, and the materials that can have performance that is adaptive and responsive and self-optimizing, we need to learn from nature. And in this way, we can do a couple of things. We can either study biological systems and just understand what is happening with them. You can stop at this moment if you want. But better than that is actually to define the importance and the role of the nanoscale in their design. And then, hopefully, to design these bio-inspired materials based on this knowledge. So overall, if you ask me, I think that the objectives of interesting things is multidisciplinary by definition. And if we combine nanotechnology with biology and with physical sciences over here, where they all collide together, really interesting things may happen. And I mentioned it already in the previous slide. You should start with search for interesting biological systems that can teach you something. I'm in particular interested in what I would call high-tech properties. In particular, I'm less interested in biology itself. I'm interested in what nature can tell me about magnetic materials, electronic materials, mechanical or other high-tech properties. And even that is already extremely rewarding experience, because actually you don't have to search. Any organism can teach you something exceptional and interesting. But what becomes difficult is understand the mechanisms of what nature has evolved to create these interesting structures. It becomes even more difficult to identify kind of new things that we have never thought about before, and combine these things maybe even with existing techniques. I'm not saying that biology alone can solve all our problems. We're actually really good in nanotechnology and coming up with our own ways of what is so far top-down manufacturing. But now combining top-down manufacturing of nanotechnology with bottom-up synthesis that nature can teach us can give us really interesting things when we integrate them, and then we apply. You actually can apply it anywhere you want, and I will try to show some examples. But first I want to say it's really cool area. So much can be done. There is, of course, you need luck. And of course, you need some knowledge, but in principle, really interesting things happen at this intersection between biology, chemistry, physics, design, and all of that together with nanotechnology. So let me just try to divide my presentation. I probably will go very fast because there is no way I can cover everything I have there now, through a couple of chapters. And I will just present different things that my lab is trying to do, not everything that we're trying to do. And I'll start with what we call how to solve sticky problems in our life. And by sticky, I mean a whole range of things. It's either icing, but also contamination and contamination of solar panels or windows, or marine fouling, or even graffiti is an unpleasant contamination. You can go to further things that are also important to this country, in particular oil transport, or infestation and medical devices. And these are completely different areas, but I'm not a biologist. I'm a physical scientist, and physical scientists have the tendency to reduce the complexity to the range of manageable parameters. So if I would look at this complexity and I would say, what is common between these completely different phenomena? Common thing, as trivial as what I would now say, common thing is that in all these cases, there is accumulation of unwanted material on the surface, different material and different surfaces. But we want to avoid and prevent these materials from contamination. So what can we do to solve this problem? And I will show, again, just a couple of these more extensively. This is my group 2 years ago, and I actually mostly show this to countries not like Canada, because you know what I'm talking about. This is ice. Look at this. This is Harvard. This is pile of snow, which is this person over here, Dutch. He is 2 meters, 5 centimeters tall. And this pile of snow is about twice, he's standing not on the water, twice taller he is. And look at these icicles that are huge. And if you think that this is pile of snow, no, this is a car. And this is just next street to Harvard. So obviously, icing is a problem. And even if we don't talk about these cases of icing, and simply think about refrigeration, and think about energy and what we need to, how to improve energy, we have to look at these slices and see that simply refrigeration is 4% of the energy, and out of refrigeration, defrosting cycle takes a lot of energy. I can go further. I just decided to choose 3 examples. There are many more. Marine fouling, yet another thing that we don't have solution yet for that incredible problem. And depending on the type of fouling, whether it is soft fouling, light slime, or soft fouling, more severe fouling, or heavy calcareous fouling, if you look simply on how it affects simply penalty for fuel expenses alone, it gives you huge penalty that we need to address. And yet another one that I will put here would be infections. And again, I was really surprised when I learned at a certain moment that nosocomial infections and nosocomial infections are infections that you acquire in the hospital. So you go to a hospital with something you have, you want to be treated for one thing, and you pick up nosocomial infection. And these are very pronounced, and these are about expenses, costs of that, estimated as about $5 billion US. And I'll skip that one. And what do we do when we think about it? And one of the strategies that's been around now for some time, of course it's been around in nature for really long years, is what we call lotus effect. And lotus leaf has this amazing feature that if you have nanoscience invented by nature, if you have a structured surface, ideally on the micro and nano scale. And even if it's on micro scale, it has to have nano features in addition to that. Then water droplets would actually roll off the surface because the water would have nearly 180 degrees apparent contact angle because it's sitting on a cushion of air. So when compared to hydrophilic surface, you drop the droplet, it spreads, it's always in contact. Or hydrophobic surface, it's less in contact, but still in contact, but super hydrophobic. Droplets of water jump off the surface, leave it as it was before without contamination, and it's kind of a nice way to do it. However, if you change a little bit something in this system, and this is one thing that I often tell my students and those who are interested in biological inspiration, choose the right inspiration, because nature evolved this to deal with water and to deal with water in warm countries or warm places in the world. Which means that if you have, instead of water, low surface tension liquid, I'm not sure how to play this, I hope it will play. So water is jumping off the surface, but if you have alcohol rain, would be nice if we would, but nature didn't evolve for that. You could see the color change. We'll get back to this beautiful star of my presentation, this butterfly. Again, later on, you could see wetting occurs. It's actually not preventing from wetting. So low surface tension liquids, failure. High temperature, also failure, because at high temperature, even water has low surface tension. Contamination, high humidity, icing, it fails. So lotus leaf and superhydrophobicity is not a good inspiration if you want to solve problems of serious contamination by anything but water. So the other plant that we used as an inspiration is this plant, pitcher plant, this carnivorous plant. And it is really lazy stuff. It wants to eat, but it doesn't do anything for it. So on dry day, all these insects are running around. On a wet day, they cannot stay on the surface, they slide in. So it doesn't even have to capture food. The food is coming in the stomach when the plant is hungry. So if you look at the structure, nanotechnology is again here. So what is happening is that the way these insects attach to surface is either by these hooks that often have these nano features on them, but even more importantly, in addition to this mechanical hooking, there is a pouch of oil. And if we look at the surface, it's nanostructured surface, and in fact, very similar to lotus leaf. But something different is happening here. And what is actually happening is that this surface is not hydrophobic, as it's supposed to be in the superhydrophobic surfaces. It is hydrophilic. So what happens then is, just like superhydrophobic surface makes droplets of water, superhydrophilic surface, meaning that it's structured hydrophilic surface, picks up the layer of water and creates a film that covers the underlying substrate. So what happens then is that you create a solid that is protected by a liquid. And in fact, it doesn't have to be this example of pitcher plant that coats it with water and at this moment ends would slide out. This is very common strategy in nature because nature uses it in our stomach, in the gut. There is a nanoscience there on the wall, and then it keeps a mucus layer to make it slippery, because liquids are slippery. Or our eyes, this is actually eyes of my grandson, or if everything is fine, they're coated with a layer of a liquid. So to provide these cleaning properties. Or fish. swims faster because scales of fish are nanostructured. So what can we do here if we want to use this idea? And the idea is really taking this idea from nature and create what we call slippery surfaces, slips, which is liquid infused porous surfaces, and porous in particular nanoporous. And they're absolutely perfect. They're pressure stable, they do everything that superhydrophobic surfaces can do. And if you design those, and you've probably seen the poster by Rina, who was a co-op in my group, by the way, is when you do it properly, then everything slips from these surfaces. So it is very counterintuitive concept. And this nanotechnology is all over it, because conceptually, when we try to reduce drag, or when we try to reduce friction, what we generally do is polish things so that it's not structured. The more structured it is, the more friction it is. So what we do here, we have to have nanostructure, but the nanostructure here, so in a way you use roughness, use nanostructures to create ultra smooth surfaces. This is counterintuitive, because your nanostructure, what is it doing? It's capturing the liquid, doesn't have to be water, as it is in nature, that provides a shielding from contamination medium. So in this way, you can have all kinds of nano approaches to make your substrate, or any material that you want can be structured to hold lubricant and repel whatever you want. And the outcome of that is that you have nanocapillarity, because you have a nanoporous surface. This gives you high capillary force to keep the liquid inside. You have chemical affinity, and these materials really give you lubricant at the top, and everything slides on liquid surfaces. I'll skip that. They are self-repairing, because the active part of your surface, now not a solid, that's very difficult to repair, but a liquid. Because if, and this is an example of crude oil is important in Canada, this is superhydrophobic surface, this is slippery surface. You cut it, doesn't care about it, immediately it recovers it, because liquid can reconfigure and heal, repair this site. There are many other things, and again, if we want to talk about oil, you can design it in any way you want. You want it to withstand high temperatures and play with oil. Here is an example, again, superhydrophobic surface, slippery surface, 200 degrees C. It's boiling, but it's not contaminating the surface. Or, if we go back to icing problem, again, this is regular aluminum from which refrigerator coils are made. This is aluminum that is made into slippery aluminum, something developed by, at least this part, ice work by Mike Creda from Waterloo, and a couple of other things. Then Rina was doing in my lab as well. Still waiting for your paper, Rina. And icing can be, at least frosting can be done, and it's something for fun. You want to protect from graffiti. There was a filming in my lab that you use graffiti, it contaminates the regular side, and only half of it is slippery. And then I've done that, and Harvard's still very upset that I've done that to Harvard's sign. But you clearly see that you can create these things, and there are many more, and I will skip some, but I will still show some. This is an example of blood. This is slippery surface. Middle is superhydrophobic surface. Bottom is nicely polished glass slide. And sometimes students would say that I'm insisting on some experiments that I don't trust them. I trust them, believe me, but sometimes those who see our results may not believe to what we are showing. And therefore, I often ask to show experiments on the same substrate, not two different experiments, then you never know what was done and what you compare. And this is their same substrate, and you could see nothing is happening on the slippery surface, highly contaminated, super hydrophobic surface, and so on. And you can think about bacteria or algae. Here's another example. On the same substrate, you pick it up from algae. There is an algal film on the regular side, nothing on the slippery side. And so on, and we can continue. And one of the things that we just recently done is trying to apply it, and in particular, taking on difficult problems. If we think about medical problems, or marine fouling problems, or icing problems, to me, these are really critical and interesting as a scientist, because we have no really good ways to solve this. And here is work that was done by quite an army of Waterloo co-op students on looking at on blood on slippery surface and non-slippery surface and the amount of bacteria. There is a bar here. It's so small that you don't even see it as compared to controls, and all kinds of interesting things in medical area, including our recent paper in PNAS, where we actually have done studies in pigs, looking at the endoscopy, bronchoscopy procedures. And with these procedures, we found that compared to regular bronchoscope, which gets dirty immediately upon exposure to blood, and it takes minutes to clean the bronchoscope, while slippery bronchoscope would either not get at all fouled, or fouling will disappear on its own within seconds. Just it would slide off. And there's a movie showing that you even put it inside blood. There is this endoscope here, blood is bleeding here, and you still see everything. While if you do this with a regular scope, the moment you remove it, you will never see anything. And in this case, dipped in blood, removed, you see everything, no contamination. Or yet another one in this area. Recent paper in Science, just a couple of months ago. This is slippery surface, this is slippery surface. These are surfaces, control surfaces of different kind. For example, there is a toxic paint that is commonly used these days. This is commercial paint that is now, this is regular control, this is slippery coating. And it works. Actually, some of them are already 2 years in the ocean, and they're still performing very well. So let me finalize this by saying it's not only applications. And I know you are all interested in applications. I'm actually interested in applications, but wouldn't say even more so, but I believe that our ability to create new technologies and do many interesting things would still require very deep basic science. So my group is also involved, definitely involved, in trying to understand what is going on in these surfaces. And here is an example of actually thinking about the mechanism, why liquids would move around so easily on these surfaces. And again, this paper that just came out this month in Nature Physics, and one of the authors is in the audience. Seneca is here, and Ru Ping is also the two students, co-op students on this paper. And the outcome of that, many things. But one of the things that is important to this crowd, and there is a lot of discussion of entrepreneurship and what to do, we did start a company, and Rina represented this company today here. And what is important that we now can do it on any material, whether it's fabric. The sleeves here are made of slippery sleeves. And Pua Tak Singh, who invented this technology, everybody was throwing everything at him. And the idea was that everything is contaminated except for this sleeves. We can do it on metals. We can make it extremely mechanically strong, as this example. You can scratch it and it's still slippery. You can do it inside the catheter. You can do it on entire, let's say, refrigeration coil. And of course, we're still interested to understand why it's like that, and we would be really happy when SLIPS technologies would do something with this and actually turn it into the product. Now, chapter 2, I will go very fast through other chapters. The time I spend on the chapter is not in correlation with how I like this subject, because it just depends. I removed the number of slides not proportionally in my presentation. And as you could see again, I use the same butterfly. And the butterfly is used now also because of the wetting properties, but to show something else. I'm sure many of you know that the color here arises not from chemistry, well, still from chemistry, because everything is chemistry. I'm a chemist, I'm supposed to say that. But it's actually physical color, or in other words, structural color. So the color comes, just like in opal, it comes from regular arrangement of either spheres or pores, in this case, structures, but there are other butterflies where this is arrangement of empty spaces. And something interesting, the fact that this one, when it's hydrophobic, repels water, but the same one doesn't repel alcohol, made Ian Burgess, my contribution was very small, but made Ian come up with some idea. I remember I said, probably it's not going to work, and Ian didn't care what I said, of course, and he immediately went to the lab and tried. And what he did was to somehow combine it with another paper that I published when I was at Bell Labs at the time, where I was studying this brittle star. So it had a very strange feature. It would change color from black to white. And the only description at that time in biological literature was that it's yet another example of mimicry. So it changes color in response to environment. So my take on that was, that's absolutely crazy, because this brittle star is actually black during the day and white during the night. If you want to mimic the environment and escape this way, you would be white during the day and black during the night. So what appeared to be the reason for that is, in fact, that it had an array of lenses on its skeleton, and there was a pigment and a porous network, and this pigment will cover the lenses during the day and really acting as sunglasses for the organism to change the intensity of light that would come into the system. So this idea of multidisciplinarity, I honestly think neither chemistry alone, nor physics alone, nor biology alone can do most interesting things are when they come together and you combine different things. Oops. So, doesn't matter. What I wanted to say, that this organism is optimized for microfluidics, optics, and mechanical properties. So what Ian decided to do is to first, based on the work of another Canadian, Ben Hatton, who was my postdoc at the time I was at Bell Labs and then moved with me to Boston, is how to make these structural color very regular crystals. But then, maybe because Ian heard too much of importance of chemistry in my lab, just that is simply structural color. But if you now locally encrypt chemical information into this photonic crystal, so that certain regions are hydrophobic, others are more hydrophilic, and you can play with different molecules to achieve that, then you can create a photonic crystal that is dynamic and in changing its properties in response to the liquid it is exposed to. And this example, oh, okay, it's playing, I thought it wouldn't. And since everybody knows that I'm a crazy scientist and I love anything that lives in the ocean, one of the first things that they've done, they made these beautiful blue things, and they added I forgot what it is, water or alcohol, doesn't matter. And then you see here is a brittle star or starfish, here is whale, here is crab, and here is fish. And it's fully reversible, and it's a wonderful approach that then we took it and started to play with that and done all kinds of things in really putting information inside, multiple levels of information, and depending which liquid you would use, you would see something different. And of course, we started with acknowledging the funding agency, and the funding agency was Air Force, so we had to take a butterfly and tattoo it with US Air Force. And you could see these letters are blue, because liquid doesn't go there, and everywhere else, blue color is disappearing. Here is another example of you don't see anything here, but the moment you add the proper liquid, letter H will appear as if you would never know it's there, but again, based on the same principle. And yet another one, I don't know whether it will play. Yes, it plays. Is a project with School of Design. I didn't mention yet that architects might be interested in things where the properties originate on the nanoscale. And I actually introduced a new class, joint class between School of Engineering and School of Design. Now it's actually a new degree, which is called Nano, Micro, Macro, where we show the properties of macroscale properties. And this particular thing was done as an example of tiles in your bathtub. You're taking a shower, it shows something beautiful, and then it's dry and it's gone. But of course, there are more interesting things that one can do with that. Yet another example, Ian was thinking about anti-tampering. What if your chemistry is not neutral? It's actually interacting and reporting on something that is happening. And this work was also done by co-op students and Ian, where you can, from the wetting pattern, tell you history of exposure of how much light, for example, your package was seeing. What if it's a drug that it was not supposed to be exposed to light? And you can say, by looking at this wetting pattern, and there are other things that now being done in our lab, very important thing, talking about blowing up of trains that carry oil. And we continue to work with Ian on this project and thinking how one can create a sensor that simply dipping it into oil sample, one can tell which group it belongs to and therefore knowing how to package it. Okay, a lot of drinking. And this is a big problem, by the way, with you guys coming to my group, is that actually, I have no idea what it is in Canada, but in the US, drinking age is 21. Our group is doing a lot of that, and some of you guys coming from Waterloo are below this age, and that creates some potential problems. I love this one because it's chess set where the color comes from photonic color, and you have no idea which piece this is unless you put the liquid, and very special liquid in this case. So let me, and Ian started a company. It doesn't matter that it's not doing that anymore, but it's, of course, at the beginning created their own shot glass that depending what you put, either showing letter V or validarium. So in the last 2 minutes, I'll spend on other chapter. Dynamic materials is extremely interesting project in my group. So what I'm doing is I'm trying again to find common features in completely different organisms. So what is common between Venus flytrap or these wheat awns or the flowers themselves, or sea urchin have these constantly opening, closing structures, or even if we talk about cilia and flagella, somehow it's not moving. But common feature and simple feature to me is that it has high aspect ratio, hairy surfaces at the nanoscale, and they're put in motion by a muscle. And what if without complexity of biology, we would use this simplified method and simply what we call making hairs. And hairs is hydrogel actuated integrated responsive structures. And it's really using gel as a material to change the hairstyle. And we take using nanotechnology. We make high aspect ratio. In this particular case, they're about 200 nanometers in size. And we add a muscle, a hydrogel, that moves them around. And in this way, many things can happen. Just to give you an idea about some of them, this is a project that is now being picked up, thank God, by a couple of students because it was almost ready, and then Phil Kim started a slips technology company and left me with some of these projects unfinished. But this is a project on dynamic windows that change their reflectance in response to temperature outside. When it's high, they're coated with a thin layer of reflecting material. They're fully reflecting. When it's low, they stand up and all the light can come in. Or here is another example that simply actuation of these hairy surfaces can reveal words coming from nowhere or changing color. This is real-time movie of about 200 nanometer hairs that, due to the changes in humidity, would organize in patterns, and patterns then change their color. And there are many other things here. Yet another chapter, and I will show you just one part. And this is work that I've done originally at Bell Labs, where this sponge is fully made of glass. Skeleton of this sponge is fully made of glass. And we had a couple of papers, one in Science, one in Nature, looking at this organism. And I thought that I know almost everything about it because we looked at how it is optimized in terms of strength and fiber optics. It actually has beautiful fiber optical network. And this organism is 500 million years old. And we think that we invented fiber optics. But actually looking at the structure of this from nano to macro scale, let's forget it, the movie doesn't play, so it doesn't matter. Maybe it would, but really taking this, about that size of the sponge, and decomposing, going from large scale to very small scale, and showing how suddenly nanoscale will emerge, and where there is extremely interesting complexity of the structure that ends up with pretty much the strongest glass material that exists, and nature has invented it a very long time ago. And let me finish with this, although it sounds strange, but I would finish with flowers. These flowers, all these flowers, are smaller than human hair, very small. And there was a Nature paper, which is very nice. Sorry, Science paper. 4 years ago, and everybody was saying, who cares? Who needs flowers? Well, okay, flowers, first of all, we can make them in any shape we want, and they're beautiful, and they're all extremely small. And this year, we have another Science paper, actually to show that when you know exactly mathematical principles of how these shapes emerge from the nanoscale, and the only thing we do to create all these complex structures is by mixing two solutions. No top-down manufacturing, etching, nothing of that kind. They just emerge. Then, from this mathematical modeling, we were given interesting shapes and how to get to these shapes. And in particular, some of these shapes were shapes that one can use in beam splitting, in optical devices, and we have shown that indeed we can create beam splitters and they would conduct light very nicely. So one can, just by mixing two solutions instead of flowers, to get something potentially useful. So let me finish with again showing the idea of a dream house, and indeed thinking about all these properties that I mentioned before could be, and should be, in my case, as a suggestion, be inspired by things that nature has already evolved. And then coming back to objectives of bio-inspired nanoscience, just combining nanotechnology with biology and physical sciences, and actually think about broad range of things. You don't have to follow one organism for any good idea. Combine these organisms. Doesn't matter that nature may not combine two ideas in the same creature. Combine them. So many of the things that I've shown to you would come from completely different organisms, but some fundamental principles could be used, and interesting ideas will come out of that. So I'd say it's useful, it can give you something, and it is fun. Thank you.
Joanna, thank you so much for your excellent talk. First, I'd like to offer you something native to Waterloo, the Canadian goose.
Thank you.
Thank you very much. And we've got also a gift from the WIN. Dr. Mithra will be giving that to you now.
Thank you.
Thank you so much. You are really an honorary member of WIN, because Waterloo grads are there and telling us that Waterloo grads are better than Harvard. That itself makes it good.
Don't put it on the website. By the way, Jatin is one of my students, and he just will almost online already a paper that he is part of.
Very good.
Thank you. Sure, we can take any questions that the audience has. You can just raise your hands. You have a question there?
Yeah, so has any lubricant shown more promise than others for the slips?
It depends. Oh, I have a mic actually. It depends what you want to do. So it's really should be considered as a platform technology where you design your system. It has multiple components, and depending what you want to repel, so there is no single answer to this question. For example, if you deal only with ice, I would choose very specific type of lubricants. For example, mineral oil would be better than anything else. Plus, it's something that is biocompatible and whatnot. But in other cases, would be a different. So it's really system design. And this is another interesting approach in material science and chemistry. Not to think about one material is unlikely to give you what you want. You may need to build it up from components.
Okay, we can take one last question. Any others in the back that I can't see? Anyone else? Oh, we have one question there.
These like slip systems, they seem like they have to have some sort of lubricant, right? That's how they work. So could you only ever implement these systems in like an environment which allows for some lubricant to be on the surface, or could you see it going past to be able to implement these into an environment where the like moisture, I guess, on some level is not permissible?
It's a very good question. And again, there are two ways to think about applications. You can start with an interesting science and then see where it could be used, or you can start with application up front. So depending on the application, if you do it, and slips is actually would be nice to do it the other way around. Depending on application, you will build it in a different way. For example, let's say you want to do it in open air and the conditions are not perfect for other things that slips can do. However, you can use other approaches. For example, what if, of course, molecules evaporate. So your lubricant would be gone, it's not going to work anymore. However, nature use vascular system. We are full of vascular system in our body. So if you now add this component, so somewhere through your slippery surface, you have arrays of channels that would fill the interface with your lubricant as it's been consumed or evaporated, this is the way to go. So if you begin with a set of problems, questions, materials for which you need to design it, and you go back how to optimize the system to solve this problem, you can add other features. I didn't mention all of them. We have dynamic slips that is slippery in one condition and completely non-slippery in another condition, but it really depends. yet again, it's not one single answer to this question.
All right, and with that, I'd like to thank Joanna once again. Thank you. And so now, as you may know, this is the point where we can explore different things. So either we can go to 1502 to see a talk by Dr. Farnaz Nouri from Berkeley, or Shakir Lakhani from Avro Life Sciences. So you can go to either room. So 1502 is downstairs and 2502 is upstairs. And on your way out, if you haven't grabbed a journal yet, please do. We still have a few remaining. So help yourselves to those. Thank you.